In this lesson, we're gonna write the selection sort algorithm in Java and see how it performs on large arrays. We will test the algorithm by giving arrays of different sizes. We will start with small arrays and then gradually move to larger ones. Each time we run the algorithm, we will check how long the algorithm takes to sort the input array. We have already prepared an empty project in IntelliJ with only the main class. First, we're gonna add a new class to the project. In this new class, we will create a few helpful array utility methods. And then after that, we will add the selection sort algorithm as another method in the same class. So let's get started. Open the project tool layout, expand the project, go to the source folder, right-click, select New, and select Java class. We need to give the class a name. We will call it Array Utils, which is short for Array Utilities. Press Enter. We will enlarge the font and we will start writing the methods. The first utility method we need to write in this class is a method that creates a new array filled with random values, using the size and value range specified as parameters to the method. The method will be static, so we call it directly from the class, without creating an object from this class. We will call the method makeRandom, typing public static, and since the method will return an integer array filled with random values, so the return value will be an array of integer and the name will be makeRandom, and the method expects three parameters. First is the size of the array as an integer. Second is the starting value of the range also as an integer. And third is the ending value of the range also as an integer. Inside the body of this method, first we create a new integer array that we will call it list, with the size given by the user. So an array of integer, we call it list, equal to new int size. Also, we need to calculate how many possible values are in the range from start to end. And this value will be saved into an integer value, we call it range, which is equal to end minus start plus 1. We add 1 so the end value is included. Next, we write a loop that will go through every position of the array from index 0 up to the last index. For integer I equals to 0, I less than size, I plus a plus. In each iteration, we generate a random number and save it into list of I. So list of I is equal to. Now we will write a formula that will generate a random integer number within the range from start to end. The formula is typecasting integer range multiplied by the random method inside the math class plus the value of start. Math.random gives a value between 0 and 1. Multiplying by the range stretches this random number into the range we want. Then we cast it to an integer and add the start value so the final number is within the correct range. We store this random number in the array at position I. Finally, we return the completed array filled with random values by writing return the value of list. This completes the implementation of makeRandom method. The second utility method we need to add to this class is a method that prints the contents of an array on the screen. showing the values line by line based on the number of values we want to display per line passed as a parameter. This method is also static. So public, static, it returns void because it is going to print, and it is called the print. The method prints the contents of an integer array. It takes two parameters. First is the array itself, so integer array list, and the second is an integer for the number of values we want to print on each line. And this will be an integer, we will call it per line. Next, we need to write a loop that goes through every element in the array, from index 0 up to the last index. For integer I equal 0, I less than list dot length I plus a plus. In each iteration, we need to check whether we should start a new line or not. And this can be done by an if statement. So we write if the value of I mod per line equals 0. Then we print a new line, system.out.println. This if statement checks the current index, which is the value of I. If it divides evenly by per line, then it prints a blank line. This makes the output neatly well arranged with the desired number of values per line. After that, we need to print the value at the current index. So we will use a printf, and inside we will write %6d, and we print the value of list I. We use a printf to format the number, so it takes up 6 spaces, which helps keep the columns aligned. This completes the implementation for the print method. After writing the two utility methods, let's write the algorithm for the selection sort. This will be written below the print method. It will be public. Also, as a static method, it returns nothing, and the name will be selection sort. It takes the list that will be sorted as input parameter, and we will call it list. We have already studied the algorithm, and we're going to write it in Java. So the outer loop for integer I equals to 0, I less than list dot length minus 1, I plus a plus. In each iteration, we store the value of I into min, assuming that the first element at index I is the minimum, and then we have an inner loop, which is j starts from I plus 1, j will be less than list dot length j plus a plus. In each iteration, we check the value of list of j. If it is smaller than list at minimum, then we need to change the value of minimum by the value of j. After exiting from the for loop, here we need to swap the value of list I with the value of list minimum. This can be done by having a temporary variable integer, we call it t. We save the value of list I into t, and list of I will be equal to list of minimum, and list minimum will take the value of t. So for swapping, we need 3 assignment statements. This completes the implementation for the selection sort. We will test selection sort in 2 stages. First, we write a small program to make sure our implementation works correctly by sorting a small array and checking the result. Then in the second stage, we shift to performance testing. we sort much larger arrays and measure how long the algorithm takes. This helps us see how selection sort behaves as the input size increases. So let's get started. We click the main class tab to go to the main class, and then inside the main method, we begin our first stage program. We will generate a small array, displays it before sorting, run selection sort on it, and then shows the result. So let's begin by creating our array. Now inside the main method, we create a local array of integer. We call it list. Then we call the makeRandom method from our array utility class to generate a list of random numbers. Array utils dot makeRandom. In our case, we will generate an array with 20 integers. So the size of the array is 20. And each value will fall somewhere between -1000 and +1000. So the range will be from -1000 up to 1000. Before we sort anything, we want to see the original contents of the array. So we print a message indicating that this is the array before sorting. And then we call the print method from our utility class to display all the numbers on the screen, 15 values per line. So we print this message, sout. The message will be the array before sorting. And then we call the method print from our array utility class. Array utils dot print. We supply the list as an input parameter, and we want to print 15 values per line. So the second parameter will be 15. Now, right before we begin the sorting process, we print also another simple message to let the user know that the selection sort is about to start working. So after this line, we need to print a message that says sorting has just started with some dots. Now we call the selection sort algorithm from our array utility class and pass in the list we just printed. So array utils dot selection sort, and we supply the array list as input parameter. Once the sorting is finished, we need to print another message to indicate that the process is complete. So we print the message, and the message says sorting has completed. To make sure our selection sort method works, we could print the whole array and check it by hand. I mean by looking at the output. But that only works for small arrays, and with large arrays, that's not realistic. So first, let us print the array and check by looking at the output if the array is sorted. And then after that, we will make a utility method that can automatically help us check if this array is actually sorted. Let us print the sorted array. Array utils dot print. We supply the list, and we want to print 15 values per line. This completes the implementation of our starting program. Now let us run the code to see the result by pressing Shift F10. This is the output of the program. As you can see in the output, the program displays the contents of the array before sorting and after sorting by printing 15 values per line as specified in the print method. But there is a slight problem on the output. Notice that after printing the content of the array, the print method is not adding a new line. This makes printed messages after calling the print method not printed on separate lines. So let's go back to the utility class and modify it to add a new line after displaying the content of the array. Close the output screen, go to the array utility class, go to the print method, and at the end add a new line. Now go back to the main program and run the program again. Now from the output, we can manually tell whether the array is sorted by scanning through the printed values and checking if each element is smaller than the one next to it. But as we mentioned earlier, that approach isn't practical for large arrays. So let's go ahead to our utility class and create a method that can automatically verify whether the array is actually sorted. Here we are now in the utility class. We go to the end of the class to define the new method. We start by declaring the method header as public static method named isSorted. That takes two things, an integer array A and a boolean ascending. It returns true if the array is sorted the way we ask, I mean ascending or descending, and false otherwise. Public static boolean is sorted. And the two parameters will be the array, we call it A, and a boolean variable, we will call it ascending. Inside the method body, we start a for loop with index I from 0 up to one element early, which is a.length minus 2. We stop one element early because we will compare each element to the next one, I mean AI with AI plus 1. Or integer I equals to 0, I less than a.length minus 2, I plus a plus. Inside the for loop, we check the ascending flag. If it is true, we want to verify the array is in non-decreasing order. So we write f ascending and we open curly brackets. Inside the ascending branch, we test if the current element is greater than the one next to it. If that ever happens, the array is not sorted ascending. So we write f ai greater than ai plus 1. Then we return false. So if we find such a violation, we immediately return false. No need to check further. Now if the check is not ascending, I mean if ascending parameter is false, then we expect descending order. So we write else. And inside the descending case, we check the opposite. If the current element is less than the next one, that breaks descending order. So we write f ai smaller than ai plus 1. Then again, we return false. If we exit the loop and reach this line, then no violations were found. So the array is sorted the way we asked and we return it true. So we write return true. And that finishes the method. Now let's go back to the main program. We are back to the main program. To check whether the array is sorted using isSorted method, we go to the end of the program after printing the array and simply place the method call inside an if-else statement. So we go to the end, we write f, we call the method arrayUtils dot isSorted. We give the list, which is the array, and the second parameter is true. We want the method to test if the array is sorted in ascending order. If the return value is true, we print a message, the array is sorted. Otherwise, we print a message, the array is not sorted. So let's run the program and see the output. Shift F10. As you can see, the utility method confirmed that the array is sorted, which shows that our selection sort implementation in the utility class is working correctly. And this completes the first stage of our evaluation. Now let's move on to the second stage. In this stage, we're going to write another program to test the performance of the selection sort algorithm. And we're going to do that step by step. We will generate large arrays filled with random values. We will not print these arrays because they are huge to be printed on the screen. Instead, we will focus on timing the sorting process. This will be done by using the Java nanotime method. We record the time right before we start sorting. Then we run the selection sort algorithm. And as soon as it finishes, we record the time again. By comparing these two timestamps, we can figure out exactly how long the algorithm spent sorting the array. This gives us a clear look at the performance of the selection sort when working with large datasets. So let's get started. For the performance run, we will create a large array with 50,000 random values, ranging from -1,000 up to 1 million. So inside the main method, we define a local array, we call it list. We will call the method makeRandom that we have defined inside the array utility class. Array utils.makeRandom. And the size will be 50,000. And the range will start from -1,000 up to 1 million. Notice that in this range, we are generating more positive numbers than negative numbers. Also, we are spreading the range to 1 million. Also, we are spreading the range to 1 million so that we have less probability of generating duplicate numbers. After creating the large array, we need to record the time just before calling the selection sort. So print a message to let the user know that sorting has just started. After creating the large array, we need to record the time just before calling the selection sort. So let's print a message to let the user know that sorting has just started. Sorting has just started with the 3 dots to let the user tell the user to wait for sorting. And immediately after that, we record the time as the starting time for sorting and save it into a variable. We will define a variable start as long integer equals 2. To record the current time, we call the Java system nanotime method. So we write system.nanotime method. The return of the nanotime method is a long integer. That's why we have defined the starting time as a long integer. Let's talk briefly about the nanotime method. For more precise measurement of elapsed time independent of system clock changes, system.nanotime method is recommended to use. It gives us the most precise timer the system can provide, measured in nanoseconds. We mainly use it to measure how long code takes to run with very high accuracy. Which is perfect for benchmarking. Algorithms or timing small pieces of code. Now we call the selection sort method to start sorting the array. From array utils class, we call selection sort and we provide the array as input parameter. After returning back from the selection sort, we need to record the time again as the ending time of the algorithm. Long, we define the variable end equals to system.nanotime. Now we need to print a message to let the user that sorting has just finished. System.out.print sorting has finished. After obtaining the algorithm's start and end times, we can determine the elapsed time by subtracting the two values and displaying the result. However, Printing this raw value in nanoseconds would produce an extremely large and unreadable number. Instead, we will convert it into milliseconds, seconds, minutes, or hours, whichever is most appropriate. And to do this, we will create a helper method beside the main method that takes a time value in nanoseconds and formats it into a human-friendly form. Let's walk through the code of this method step by step. After the main method, private static void print elapsed time, this is the name of the method, followed by the single parameter as a long integer, we call it nanotime. Here we are defining a private static method called print elapsed time. It takes one parameter, nanotime, which is just the amount of time measured in nanoseconds. The first thing we do is convert nanoseconds to milliseconds and save the result into a variable, we call it milliseconds. Double milliseconds equals to nanotime divided by 1 million. Since 1 millisecond is 1 million nanoseconds, that's why we divide by 1 million. I'm storing the result in a double, so we keep the decimal detail. Now we start checking which unit makes sense. We start by testing the value of milliseconds. If it is less than 1000, which is equivalent testing if it is less than a second. If the time is less than 1000 milliseconds, then we need to print it in milliseconds. And we do that by using a printf to show the elapsed time in milliseconds with the 3 decimal places followed by the word ms, which is short for milliseconds. So printf, we print elapsed time followed by the time formatted with the 3 decimal places followed by the word ms, which is short for millisecond, and adding a new line. And here we are printing the time in milliseconds. If we were not under a second, maybe we are under a minute. 60,000 milliseconds equal 1 minute. So we check for that next. Else, if milliseconds is less than 60,000, which is equivalent to testing if it is less than a minute. So if we are less than a minute, we print the time in seconds. And to do that, we divide milliseconds by 1000. So we will copy the printf line, Ctrl C, and we will paste it, Ctrl V. We will change the unit of time from milliseconds to seconds, and we will divide milliseconds by 1000. Next, if it is not under a minute, maybe it is under an hour. 1 hour is 3,600,000 milliseconds. So that's our next cutoff. Else, if milliseconds less than 3,600,000. And this is equivalent testing for if it is less than an hour. If we are under an hour, we will convert milliseconds into minutes by dividing by 60,000 and then print that. So we will paste printf, we will change the unit from seconds to minutes, and we will divide milliseconds by 60,000. And if none of the previous conditions matched, that means the time is 1 hour or more. So we divide by 3.6 million to 10 milliseconds in 2 hours, and then print the result. Else, paste printf from previous copy, remove ms, and write hours, and divide milliseconds by 3,600,000. And this completes the implementation of the method print elapsed time. Let's return back to the main method and display the elapsed time between the start and end timestamps using the print elapsed time method. This elapsed time is for sorting 50,000 integers. We go to the main method and we call print elapsed time method, and the parameter will be the difference between end and start timestamps, end minus start. Now let us run the program. Shift F10. So the selection sort took 801 milliseconds to sort an array of 50,000 integers. That's actually not a bad time at all for that size. Now let's increase the array size up to 100,000 integers and run the program again. We go to the size and we make it 100. Press Shift F10 to run the program. As you can see, the sorting time is starting to increase. It took 3 seconds to sort 100,000 integers. Next, let's try 300,000 elements. The algorithm is definitely going to take a bit longer. So we change 100,000 into 300,000 and run the program again. And as you can see, it took 20 seconds, 0.3402 seconds. Alright, let's push it further and test an array of 1 million elements. We will start the run, wait a few seconds, then pause the recording while it sorts, and then return once it is done. We will go to the size, and we will specify 1 million, and run the program again. So it's going to take longer time. So we will pause the video, the recording, and then we will come back to you to see how much time it took to sort 1 million elements. Now we are back. As you can see, it took almost 5 minutes for sorting. And this time is noticeably long time to sort just 1 million integers. In real-world situations, this is far from ideal, especially since efficient sorting algorithms can handle sorting 1 million items in under a second. This experiment demonstrates that while selection sort performs reasonably well on small arrays, it becomes completely impractical for large ones. And this completes the experiment for testing the performance of the selection sort.